So, let us continue. In the last video we did some problems, so I want to continue and do more problems in this video. So, let us just start from where we stopped in the previous video. So, we have shown that in the last video we have shown some problems, we have done some problems where we had to check if some given sets are rings or not. Okay. So, let us continue, and we also check that a group ring homomorphism is injective if and only if its kernel is 0. So, now the third problem. So, I will continue the counting from that video last video. So, the third problem is the following. So, let R be a ring. So, let R be any ring. Show that R is a field if and only if and only if the only ideals in R are the 0 ideal and the full ring. Remember, in any ring the 0 ideal and the full ring are always ideals. So, if R happens to be a ring in which these are the only ideals, then R is a field, and if R is a field, these are the only ideals. Okay. So, let us solve this. Okay. So, we have to prove two implications. If R is a field, we have to show that it has only two ideals, and if R is any ring which has only two ideals, then R is a field. So, let us first assume this direction. I will assume that. Okay. So, let us assume that R is a field. Okay. So, I want to show that the only ideals in R are the 0 ideal and the full ring. So, in order to show that, let us take an ideal in R. Let I inside R be an ideal. Okay. So, suppose if I is 0, we are done. I want to show that 0 and R are the only ideal. So, assume I is not equal to 0. So, if I is not equal to 0, then there exists A in R, A in I rather, which is non-zero, right. This is the definition of not being equal to the 0 ideal. So, there is a non-zero element in I, but since R is a field, so recall what is a field? A field is a ring in which every non-zero element has a multiplicative inverse. So, and A is a non-zero element, A has a multiplicative inverse. Right. Since R is a field and small a is a non-zero element of R, it has a multiplicative inverse. So, denoted by, we will simply denote it by A inverse. Okay. So, that is the usual notation for multiplicative inverses. So, now let us see, if A is in I and A inverse of course is in R, it has an inverse in R, we are not saying it has an inverse in I. So, we have its inverse in R, but what is the definition of an ideal? If something is in the ideal and something is in the ring, their product is in the ideal. What is the product of A and A inverse? That is 1. So, 1 is in I, but if 1 is in I, then I claim I is equal to R, right. If 1 is in I, everything is in I. This is because take any small r in R, R can be written as R times 1. So, this is in R, this is in I, 1 is in I. So, R times 1 must be in I, right. So, for all R in R, R can be written as R times 1, where R is an element of R, 1 is an element of the ideal. So, the product must be in the ideal. So, for all R in R, R is in I. So, if 1 is in I, then I is R. So, we are done in this direction, right. If R is a field, we have shown that any non-zero ideal must be the full ring. So, that means the only ideals are 0 and R. Now, let us suppose that let R be a ring such that the only ideals. So, S dot D means such that the only ideals in R are 0 and R. Okay. So, let us now take this. So, the only ideals in R are 0 and R. If this happens, we want to show R is a field, and again what is the meaning of a field? A field is a ring in which every non-zero element has a multiplicative inverse. So, let us take a non-zero element, let A be in R a non-zero. We want to show that A has a multiplicative inverse, and then it will follow that R is a ring. So, to show that, consider the ideal I generated by, okay, this is new terminology, I will explain this, generated by A. So, by this I mean I is equal to all elements of the form R A, where R is in R. So, I claim that this is actually an ideal, and it is said to be generated by A because every element of I is a multiple of A. So, we say that it is generated by A. So, this is an ideal, is a simple exercise for you, which I do not want to do, and I will let you do this. It is closed under addition as you want for an ideal, because if you have R A plus R prime A, it is R plus R prime times A. It is certainly closed under multiplication by any ring element, because you take an element of this set R A, multiply by R prime. So, I will write it here, R prime times R A is R prime R times A, because of the distributive property of multiplication, and this is again in I. Okay. So, anyway the remaining details I will let you check. So, consider this ideal, this is actually an ideal I. Now, since certainly A belongs to I, right, and A is non-zero, why does A belong to I? A belongs to I because A is equal to 1 times A. So, I consists of all multiples of small a. Small a itself is certainly a multiple of A. So, A is in I and A is non-zero, I is not equal to 0, right, because it contains a non-zero element, but by hypothesis I must be R, because what is the hypothesis? Hypothesis is that the only ideals in R are 0 and R, and we have here an ideal I which is not 0, so it must be R, but then 1 belongs to I. 1 belongs to I because 1 is an element of R, I is equal to R. So, in other words, 1 has to be of the form R A for some R, right, because I only consists of elements of the form R A, and 1 is one such element. So, 1 is equal to R A for some R in R. That means A has a multiplicative inverse. Right. So, A has a multiplicative inverse. We have produced an element R such that R times A is 1. So, that means R is the multiplicative inverse of A. So, A has a multiplicative inverse. So, every non-zero element has a multiplicative inverse. So, R is a field. So, the only rings which have exactly 2 ideals are fields. So, if you have any ring which has more than 2 ideals, it must automatically be a field. Sorry, if you have any ring that is more than 2 ideals, it must not be a field. So, now the next exercise or next let us see, number will be 4, is a corollary of the previous 2 problems. So, let us say phi is a homomorphism of rings Okay. Suppose R is a field, then phi is injective. Okay, it is a good time for me to remind you that all our rings are non-zero rings. R is not 0, R prime is not 0. So, the only we will never consider 0 rings. So, every time I say a ring in this course, I mean a non-zero ring. So, here the domain ring R is a field. I claim then that the ring or ring homomorphism is automatically injective, and the reason is its kernel is an ideal of R. R is a field. So, the ideal is either, all ideals of R are either 0 or R. So, kernel is either 0 or R, but kernel cannot be R because 1 goes to 1 for a ring homomorphism and that is not 0. So, kernel is not equal to R. So, kernel is equal to 0, which by an earlier problem means phi is injective. Okay. So, this is a straightforward application of the previous two problems. So, I will not say anything more about it, but next problem, this is something that I used earlier, or I commented about this in an earlier video. So, let n be an integer, will be actually a natural number. So, it is a non-negative integer. Then we said Z mod n z is a ring, right. So, this I told you earlier, there is a ring structure on this. Okay. So, this is a field if and only if n is a prime number. Okay. So, this I want to do. So, I will not recall here, and the fact that Z mod n z is actually a ring. You can multiply 2 residue classes modulo n, or you can add 2 residue classes modulo n. The residue class of 1 is the identity element for multiplication, the residue class of 0 is the identity element for addition, and so on. So, in the sometime in the future I am going to talk about quotient rings in more general, and Z mod n z will be an example of that. So, at that point I will remind you again how to think of this as a ring, but for now suppose that it is a ring. I claim it is a field if and only if it is a prime number, n is a prime number. So, solution, and the solution is something that you can construct easily. So, I will not do all the details, but quickly tell you the basic idea. So, suppose, so in this direction, or actually in this direction. So, suppose n is not prime. So, I am going to assume that Z mod n z is a field and prove that n is a prime number. Suppose n is not a prime number, then we can write the definition of not being prime means we can write n is equal to a b, where a and b are strictly less than n, right. 4 is not a prime number because 4 can be written as 2 times 2. 6 is not a prime number because 6 can be written as 2 times 3, and 2 and 3 are. So, actually let me take n to be a positive integer. Okay. So, zero case I will separately consider. So, n is a positive integer. So, n is a positive integer, it can be written as a product of 2 smaller positive integers if it is not prime. Now, consider a bar and b bar in Z mod n z. What is a bar times b bar? The definition of product in Z mod n z means that gives me that this is a b n bar, but a b bar, but a b is equal to n, right. So, a b bar is n bar, but n bar is 0 bar because n and 0 have the same residue modulo n. So, that means a b, a times b is 0 in Z mod n z. Then, so also a bar is not 0 in Z mod n z, right, because a bar, if a bar is a 0, that means a is a multiple of n. The only zeros, 0 element of Z mod n z is the class of multiples of n. So, if a bar is 0, that means a is a multiple of n, but similarly but A is not a multiple of n because A is strictly between 0 and n. Similarly, B bar is not equal to 0 bar in Z mod n Z. Now, we claim that A bar cannot have a multiplicative inverse. In Z mod n Z. Why is that? So, suppose it has, if it has, then let us play with it. So, A bar B bar is 0 bar, right. So, that is something I commented on earlier, A bar times B bar is 0 bar. Suppose A bar has an inverse. So, let us denote that by A bar inverse as always. Right. So, let us multiply this equation by A bar inverse on both sides. So, you get A bar inverse times A bar B bar is equal to A bar inverse times 0 bar, anything times 0 bar is 0 bar. So, this is what it is, but then associativity of multiplication says that this is equal to this A bar inverse times A bar equal times B bar, but A bar inverse times A bar is 1 bar times B bar is 0 bar, 1 bar times B bar is 1 B bar because 1 bar is the multiplicative identity, that means B bar is 0 bar, but this is absurd, right. This is absurd because B bar also is not 0 element, that I have remarked here. Okay. So, A bar cannot have a multiplicative inverse. So, Z mod n Z is not a field, right. So, if Z mod n Z is a field and n is not a prime number, we are concluding that Z mod n Z is not a field. So, that is a contradiction. So, I have proved the implication to the right hand side. Now, let us do the implication to the left hand side. So, here I am assuming n is a prime number. So, n is a prime number. I want to show that Z mod n Z is a field. So, let A bar be in Z mod n Z, which is non-zero. So, I am going to bring it back to the integers and use the properties of integers. So, we have, so A bar is some element, right. We can pick any representative we want for A bar. So, we can choose a representative. Remember, Z mod n Z is the set of cosets. Any coset is a equivalence class of integers. A representative is an element of that equivalence class. So, we can choose a representative for A bar, say obviously it is convenient to call that representative A, such that 0 is less than A less than n, because any element can be any coset in Z mod n Z has a representative in the set 0 to n minus 1, but because A bar is not 0, we can choose the representative to be actually a positive number between 0 and n. Okay. So, now I am going to recall for you a property of prime numbers. Since n is prime and A is a positive number strictly less than n, A and n are co-prime or relatively prime. Okay. A and n are relatively prime or co-prime, these are they mean the same, that means they have no common factors because n is a prime number. The only factors of n are n and 1, A is strictly less than n. So, n cannot be a factor of 1, n cannot be a factor of A. So, the only common factors of A and n are 1. So, that is the only common factor of A and n is 1. Okay. But now, since they are co-prime, that means that what I am saying is that their GCD is 1. right, the GCD, greatest common divisor, is 1. That means there exist integers, let us call them x and y, such that ax plus ny is equal to 1. This can be done using Euclidean division algorithm. If you have a pair of integers whose GCD is 1, that means 1 can be written as a linear combination of those two integers. In other words, you can find x and y such that ax plus ny equal to 1. So, now consider this equation modulo n. So, that means I essentially put bars. So, I have a bar x bar plus n bar y bar equals 1, but this means, so in z mod n z this holds. So, this is in z, going modulo z mod n z, we get this in z mod n z, but n bar remember is 0 in z mod n z. So, we have a, so this becomes 0. So, a bar x bar is 1, that means a bar is a unit, it has a multiplicative inverse. So, whatever x bar is, it is a unit, it is the inverse of a bar. So, a bar is a unit, and remember we have done this for any arbitrary a bar which is non-zero. So, z mod n z is a field. Okay, so, what we have done is produced an inverse, a multiplicative inverse for any non-zero element of z mod n z when n is a prime number. So, we have shown that z mod n z is a field if and only if n is a prime number. Okay. So, this is the solution for this problem. So, let us do next problems now. So, we have done 5 now. So, go to the 6th problem. Okay. So, what is the 6th problem? So, 6th problem is about ideals. Okay. So, I am going to introduce this is a fairly easy exercise. So, let R be a ring, but these operations I am going to define are important. So, I will write it down here and leave most of the solution to you. Let R be a ring, let I and j be ideals in R. Let R be a ring and let I and j be ideals in R. So, we want to define certain operations on I and j. So, okay, so we define new ideals using I and j as follows. Okay, so the first one is it is a very simple one, it is just set theoretic, is the intersection of I and j. So, what is this? These are elements of R which are in both I and j. So, A is in I as well as in j. So, then that is the intersection. So, this is I intersection j. So, this is an ideal. So, that is the first problem. This is a very easy exercise, I will not do details. If you take two things in I intersection j, those two things are in I, so their sum is in I, those two things are in j, their sum is in j, so their sum is also in the intersection. If you take something in I intersection j and take something in R, the product is in I, the product is also in j, so the product is in I intersection j. So, this is a very easy exercise, so I will not do the solution now. So, next operation, so I intersection j. So, you can check that I union j is not in general an ideal. Okay, so this is not an ideal. I mean, I have said we define new ideals below, but I union j is actually not an ideal in general. So, as an example, let us take R to be the set of integers and I to be the ideal generated by 2. Remember, we have shown in an earlier video that every ideal in Z is generated by a single element. It is of the form 2z or nz for a positive integer n. Let us take 3 which is 3z. So, these are multiples of 2 and these are multiples of, and both of these are clearly ideals. Okay. So, now if you take I union j, these are integers which are multiples of 2 or multiples of 3. So, for example, 2, 3 are both in I union j, right. So, what is 2 plus 3? 2 plus 3 is 5. 5 is not in I because 5 is not a multiple of 2. 5 is also not in j because 5 is not a multiple of 3. So, you have 2 and 3 in I union j, but their sum is not in I union j. Okay. So, 2 and 3 are there, but their sum is not there. So, I union j is not an ideal. Okay. So, union of ideals is not an ideal, intersection of ideals is an ideal. So, let us do one operation here which is similar to union, okay, but it is the ideal theoretic union if you want to call it that. So, I will define I plus j to be all elements of the form A plus B, where A is in I and B is in j. Okay. So, this I claim is an ideal. I claim that I plus j is an ideal. So, remember again what is I plus j? I plus j is sum of things, one coming from I and the coming from j. So, I claim it is an ideal. So, this is actually once you have written it this way, it is very easy to check that it is an ideal. So, why? So, let us take A plus B and C plus D in I plus j. Okay. That means A and C are in I, B and D are in j, right. But then what is their sum? So, this can be written as A plus C plus B plus D. This is in I because A and C are in I, this is in j. So, this is in I plus j, no problem. What is their product? Actually, I do not want to take product of anything inside I plus j. So, I will take any R is an element. Let us take R times A plus B. So, take an arbitrary ring element and an arbitrary set element. So, this is in R, this is in the set I. What is R times A plus B? This is R times A plus R times B. Now, I claim this is in I because A is in I, R is in R, capital I is an ideal. So, this is in I, this is in j. So, this is in I plus j, okay. And certainly 0 is there and so on. So, all the other properties are easy to check. So, we have checked that. And now, if you think about it, I plus j is certainly an ideal. It contains the union, right. Certainly, it contains union because if A is in I, then A plus 0 is in I plus j. So, A is equal to A plus 0, right. So, A can be written as something in I plus something in j, namely 0. So, A plus 0 is in I. Similarly, if B is in I, B can be written as 0 plus B, which is certainly in I plus j. So, I is contained in I plus j, I union j is contained in I plus j. So, I union j is contained in I plus j, but I plus j can be much bigger than I union j, as this example here shows. 2 and 3 are in I union j, but their sum is not in I union j. So, we have to take the sums of elements of I and j to make this union an ideal. So, now just to complete this circle of ideas, so let us take R to be z, I to be 2z, j to be 3z as before. What is I plus j? show that I claim that I plus j is in fact all of z. Why? Okay, so let us see. So, I claim that to show I plus j is z is same as saying that 1 is in I plus j, I plus j. This is something that came up earlier. An ideal is equal to the full ring if and only if 1 is in that ideal. Okay. So, this is easy exercise. Okay. So, all we need to show, we want to show I plus j is equal to z, that means I want to show 1 is in I plus z, but then 1 can be written as minus 2 plus 3. This is in I because I is 2z, this is in j. So, this is in I plus j. Okay. So, the sum of 2z and 3z is equal to the full set of integers. The union is just some collection of integers which is not an ideal. Okay. So, this is another operation that you can perform for two ideals. I will now end this video here, but in the next video we will continue doing problems. I will give you another example of operations on ideals that you can use to produce new ideals using two given ideals. Thank you.